It's a pleasure to be here, and I thank the organizing committee for inviting me to speak about three aspects of virulence surveys that I believe can be modified to enhance our ability to manage cereal rusts. Now, my very first publication was a virulence survey on the wheat leaf rust pathogen. And afterward, I had some concerns that the results of that survey were not very useful. And over the course of my career, I kept thinking about those concerns, and it really took my whole career to turn those concerns into the three principles that I'll be discussing shortly. So, sorry it took me so long to get to the three principles. So, to put things in perspective, let's start at the beginning. Here's another picture of E.C. Stakeman. He's sitting in the greenhouse evaluating his inoculated seedlings, and this, I believe, is one of the first virulence surveys. So the things I'd like you to note here are the old greenhouse that he's working in, the seedlings that are at a very young growth stage, and each line grown in an individual pot. And he has a rather large notebook for recording copious notes. So Dr. Stakeman published his early results on physiological races in 1914. And among the conclusions that are in this publication, I believe the following are relevant to my talk today. So firstly, he found that the degree of incompatibility between the host and the pathogen varies greatly. You know, there's not black and white differences. There's all shades of gray in between. And the rust reactions can be affected by temperature and relative humidity. And these are things that we tend to forget. And although susceptible in seedling test, several lines were fairly resistant in the field. And I believe this is the first reference to adult plant resistance. And finally, a supposedly resistant variety needs to be evaluated under varying conditions in order to determine the value of its resistance. And this, to me, this seems to be a prelude to Roy Johnson's definition of durable resistance. So remember, all this happened in 1914. So let's look at the host lines that are used in virulence surveys. Originally, there were regional cultivars and breeding lines, but it was soon realized that there were some problems associated with these. Mainly, the varieties had more than one resistance gene. The genes were in different genetic backgrounds. So this led to the use of near isogenic lines, where sources of resistance were back-crossed into a susceptible, and we had individual genes in each line. And this allowed an increased understanding of reactions on individual genes. So most virulence surveys now include near isogenic lines. So regardless of the type of line used, the lines were organized into standard and supplemental sets of differentials. And periodically, additional host lines would need to be added to account for new resistances that were being used. But it's important to remember that the number of possible races is 2 to the nth power, where n is the number of differentials. So for each added differential, the number of possible races doubles. So for a set of 20 or more differentials, it's easily possible to identify millions of races. So that can quickly get out of hand. Now, the basis for this talk is explained in two recent publications in phytopathology that came out in the recent August issue. So the first is race-specific adult plant resistance in winter wheat to stripe rust and characterization of pathogen virulence patterns. And the second, characterization of stripe rust resistance in wheat lines with resistance gene YR17 and implications for evaluating resistance and virulence. So I can't tell you everything in this talk, and I'm sure I'll forget to say something that I intended to say, so I refer you to these publications for the full details. Now, for the virulence surveys that were referenced in these two papers, I went back and looked at the objectives that the author stated for doing those virulence surveys. And by far, the most common objective was to identify races. Other objectives included characterize virulence of the pathogen, determine frequency and distribution of virulence, determine effective and ineffective genes in greenhouse conditions, and detect increased virulence for specific resistances. However, if I were in charge of virulence surveys, the objective would be to facilitate development and deployment of resistant cultivars. So the principles that I'll be discussing shortly are designed to address this objective. Principle number one, for each epidemic region, the genes and differentials should match the resistance genes used in regional cultivars and breeding lines. Now, I work with stripe rust, and in 1992, Line and Guillaume identified 7 regions for stripe rust in the United States. Regions 1 through 6 are west of the Rocky Mountains, where stripe rust epidemics were common, and region 7 is everything east of the Rocky Mountains, where stripe rust occurred occasionally but rarely caused significant damage. Consequently, wheat growers in region 7 usually never saw stripe rust, and the breeders did not breed for stripe rust resistance. Now, Dr. Line worked at Pullman, Washington, which is in Region 1, and myself and Dr. Jianmin Chen, each of us got our master's and PhD under Dr. Line. Dr. Chen stayed on as a postdoc and eventually replaced Dr. Line as the USDA stripe rust expert. I moved on to a job at the University of Arkansas in Fayetteville, which is near the center of Region 7, where nothing exciting about stripe rust was ever expected to happen. However, everything changed in 2000 with the emergence of a new strain of the pathogen that had new virulence for YR9 and increased aggressiveness and adaptation to warmer temperatures compared to the old strain. So since 2000, stripe rust has been the most important foliar disease in these regions. And in the Great Plains, this region here, there's 12.5 million hectares of hard red winter wheat growing. And in southeast United States, there's about 3.3 million hectares of soft red winter wheat. This slide represents the reactions of the old strain of stripe rust on 8 soft red winter wheats and 4 hard red winter wheats. The cultivar CG514 is a susceptible check with no known resistance genes. And the top row of reactions represents the reactions on seedlings. So S is susceptible, R resistant, I is intermediate. The second row and the photos represent the reaction on flag leaves. So you can see that the seedling reaction and the flag leaf reaction agree with each other here. Now, this slide represents the reaction of the new strain on those same 12 cultivars. Usually with the new race, you expect increased virulence. But although the new strain caused severe disease on many cultivars, it was avirulent on several others. And the cultivars and breeding lines that were resistant to the new strain became the basis of breeding new resistant cultivars for the regions. Now, the reactions that are highlighted indicate that the resistance we're dealing with is adult plant resistance rather than all-stage seedling resistance. And also notice that the seedling reaction is intermediate, even though, and the adult plant reaction is resistant. So this new strain is acting differently than we might have expected. This table has the stripe rust reactions on 20 commonly grown soft red winter wheats in Arkansas in 2013. Now, I collected 8 isolates from around Arkansas in 2013, and all of the cultivars were susceptible on the first and second leaves when inoculated with each of these isolates. So there's no effective all-stage resistance in these cultivars. But yet, across several locations in the field, these cultivars are resistant or moderately resistant. We have one susceptible that not really growing much, but I wanted to include one known susceptible in the group. So the take-home message here is we have no effective all-stage resistance. And if we're evaluating races based on all-stage resistance, those results are not going to be applicable to our situation because we have adult plant resistance. Now the stripe rust genes in the left circle represent the known genes that are in the current and the previous standard sets of US stripe rust differentials. The genes in QTL in the right circle represent those that are known to be in soft red winter wheat and hard red winter wheat cultivars. There's only 2 genes that overlap between the 2 groups. And the reason that we have these 2 genes is that the breeders were interested in incorporating leaf rust resistance associated with the pleiotropic genes LR26 and LR37. So if you're using these genes to identify races, it's not going to provide very useful information on what's happening over here. Virulence to YR9 first showed up in 2000, and ever since, virulence for YR9 seems to be fixed in all the isolates. Virulence for YR17 first showed up in 2010, and its virulence is not fixed yet. So the problem here is that effective resistance genes in hard red winter wheat and soft red winter wheat cultivars differ from the genes used to differentiate races. And I believe that there are similar situations with other cereal rusts worldwide. My solution is that we should determine the genetic basis for resistance in each epidemic region, because different genes are being used in different regions. And for differentials, choose lines representing different resistant types in the contemporary cultivars and breeding lines. Now, I don't believe it's necessary that you need to know what genes are there or to have a single gene line. If you use the cultivars as differentials, you should get a more informative result as to what's going to happen in the field. Principle number 2. Intermediate reactions on host lines that had been highly resistant are important warnings of gradual increases in virulence. So if you can imagine a 0 category with no symptoms, this slide would represent the 0 to 9 infection type scale that was developed by Line and Guillaume in 1992. Now there's a 0 to 4 scale that covers a similar range, but it has a few more categories if you include all the pluses and minuses. But this particular scale can be used as a basic scale where you record a 2, 5, or 8, or you could use the expanded scale of 0 through 9 if you were interested in finer differences. Now, I'm going to show you 3 interpretations of the 0 to 9 scale, and then I'm going to ask you which interpretation is most informative about resistance of the host and virulence of the pathogen. So with interpretation number 1, infection types 0 to 4 are the pathogen is avirulent and the host resistant. For infection types 5 through 9, the pathogen is considered virulent and the host susceptible. Interpretation number 2 is similar to number 1, except 0 to 6 is avirulent resistant and 7 to 9 is virulent susceptible. Interpretation number 3 follows the original basic scale and allows for a partially resistant, partially virulent category to be recognized. So, we're going to have a vote. I want you to raise your hand as to which interpretation you believe is most informative about resistance in the host and virulence of the pathogen. So, who wants to vote for number 1? No takers. How about number 2? No takers. How about number 3? Okay, number 3 is the correct answer. However, there's a big problem with number 3. And that problem is that it's not compatible with any system for naming races. In order to name a race, the pathogen has to be either avirulent or virulent, and the host has to be either resistant or susceptible. So, what's the solution to this dilemma? Stop naming races. And use a formula to communicate virulence information. And the type of formula that I like the best is this one here. And let me explain what all the symbols mean. So first of all, you would number your differentials from 1 through last and keep them in that order. And a dash or minus sign indicates avirulence. Parentheses around that number indicates partial virulence. The number by itself indicates full virulence. And if you have a blank, that would indicate missing data. So if you did this for each isolate and grouped them according to similarities, you could think in terms of race groups. And these race groups would likely be attacking, each race group would attack a different group of varieties. Principle number 3. The method for evaluating virulence on a particular differential should predict the result of that host-pathogen interaction in the field. So there are several environmental factors that affect the infection type. So most of you know that you can't accurately evaluate adult plant resistance in the seedling stage. However, you may not be aware that some labs inoculate seedlings in the one-leaf stage and record infection type on the first leaf. Other labs inoculate seedlings at the two-leaf stage and record the infection type either on the second leaf or the first and second leaves. And there's at least one lab that inoculates at the three-leaf stage. So the difference can be significant for some host-pathogen interactions. And for some, the reaction on the first leaf is completely opposite of the reaction on the second leaf. Now, there's been hundreds of theses, dissertations, and papers about the effect of temperature on rust reactions. Yet, all of the differentials in a set are incubated at the same temperature, and different labs working on the same pathogen incubate their plants at different temperatures. Now, early stripe rust researchers quickly found out that it takes plenty of diffuse sunlight to get a full expression of an infection type. So these early workers working in a greenhouse could only work at certain months of the year to get the light and temperature suitable for stripe rust. Later, the researchers started incubating the plants in some sort of growth chamber, and then they could work all year round. However, the different types of growth chambers differ greatly in the quantity and quality of light that are produced. And the early stripe rust workers would clip off the upper leaves so that more light can get to the inoculated first leaf. Now, nobody clips off upper leaves anymore, and because growth chamber space is expensive and we're trying to crank out all the data we can, there's a tendency to cram more plants into a smaller space within the growth chamber. And this crowding effect creates serious shading effects, especially on the first leaf. So when you have all those plants together, you're not getting an accurate estimation of the infection type. 80% relative humidity was considered optimal for stripe rust, but yet many of these growth chambers have no way of controlling relative humidity. And considering that these inoculated seedlings are being incubated in some sort of controlled environment, it's reasonable to assume that the plants and the rust fungi are not breathing clean, fresh air as they would out in the field. And there's been several reports on air pollution. And of course, there's interaction with all these factors and with particular resistance genes. So the problem is that there's little environmental uniformity among labs because their facilities are different. And there's this philosophy that you can do it the way you want, just report what you do. So different labs working on the same pathogen, doing virulence surveys, have different methods. So we know that several resistances are greatly affected by the environment. So this seems to be a recipe for disaster. So my solution is that we need to determine the optimal methods for evaluating effective resistances in the region. Notice that methods is plural, because if we're working with all-stage resistance and adult plant resistance, we're going to have 2 growth stages. And for the seedling assays, we may need to incubate at more than 1 temperature, because some resistance genes are better expressed at 1 temperature than another. And to be sure that the results that we're getting in our controlled environment agree with the field, we need to do some verification of inoculating isolates on these plants and make sure that we're getting the same result in the field and under controlled environments. So for important resistant lines and important virulent isolates, I would suggest that we do ring tests among the labs working on the same pathogen group and see if the different labs can get the same results for given host pathogen interactions. So in summary, the process of evaluating the virulence of cereal rust pathogens has evolved over 100 years. And in science, evolution of ideas is a good thing, because if you don't evolve, you'll soon become irrelevant. And we need to keep the objective in mind. And remember, my objective is to facilitate the development and deployment of resistant cultivars, not to identify races. And implement the 3 principles. So the genes in differentials should match the genes in cultivars and lines. Now, I know we'll never get a perfect match, but I think there's lots of improvement for where we're at now. And we need to recognize partial virulence and partial resistance as separate categories, because they're important warnings that the resistance is being overcome. And if we heed these warnings, there's a good chance that we could substitute a different resistance before the resistance is completely overcome. And we need to be sure that the results that we get under controlled conditions accurately predict what happens in the field. And as I tell my students, work smarter instead of harder. So instead of being distracted by all the resistance genes that are known and all the possible races that might be identified on those differentials, we need to focus on the most important resistance genes and the most important virulences, and they're the ones that are important. So I'd like to acknowledge my former students, Sam Markell, Janita Stoppett, and Kevin Lee, my technicians, David Moon, Peter Roman, my collaborators, Zamin Chen, Gina Brown-Gadara, Eston Mason, David Marshall, and Ed Gabor is my statistician. Can't do anything without a good statistician these days. And my funding sources, the Arkansas Wheat Promotion Board, University of Arkansas Division of Agriculture, and the USDA. Well, I retired a year ago, and this is the sunset of my 40-year career working with cereal rusts. And it's been a pleasure and an honor to be part of the cereal rust community and to have friends and colleagues all around the world. But as I look around the room, I see that the next generation is willing and able to take over in my place. Thanks for this opportunity to present my thoughts on virulence surveys. My wife and I will be moving to Salida, Colorado before the end of the year, and my email address will stay the same if you want to keep in touch, and if you're in the area, stop in to visit. So, thank you.